Well, for section 1.5, we're going to do number 9. And we've got to graph these curves. But before we do that, let's keep in mind that if we're looking at the graph of e to the x, here it is, where this is 0, 1. And this is a graph of y equals e to the x. Okay? What if we look at the graph of y equal e to the negative x? Well, it's simply flips this graph over the y-axis. And that's what it looks like. And so this is a graph of y equals e to the negative x. Now, let's deal with this guy right here. So y equals 1 minus e to the x. Well, notice our horizontal asymptote for y equals e to the x, or y equals e to the negative x, is 0. This is going to raise that horizontal asymptote up 1 unit. And so here's our horizontal asymptote now at 0, going through 0, 1. And otherwise, it's just this graph flipped over that horizontal asymptote. And notice if we evaluate e of 0, we get 1 minus 1 because e to the 0 is 1. So the graph is going to look like this. This is x and y. Now, let's evaluate this guy. So y equals 1 minus e to the negative x. And so x and y, and we've got a horizontal asymptote at 1, 0, negative 1, or excuse me, 0, 1. And the y-intercept is, and the x-intercept are both 0, because we put a 0 in for x, we get 1, 1 minus 1 is 0. Except now we're going to take this graph right here and flip it over upside down. So there's the graph of y equals 1 minus e to the negative x. And we're done with that. Well, now we're doing question 29, and we have a population problem. And the population equation is p equals p sub alt the initial population times e to the kt, where k is the rate of change. So problem 29 says that Knoxville, Tennessee has a population of 500,000. So our initial population is 500,000. And it is increasing at a rate of 3.75% per year. So we'll turn that into a decimal, 0.0375. 0.0375. And we want to know when, how long is it going to take to that to become a million? In other words, well, let's put down 1 million. So there's our data. We're going to install the data. So we have 1 million equals 500,000 e to the 0.0375 t. And now we need to isolate t. So let's first divide both sides by 500,000. When we do that, 1 million divided by 500,000 is 2. And that equals e to the 0.0375 t. Now, we'll take the natural log of both sides, and when we take the natural log of the right, we're talking about the ln of e to the 0.0375t equals ln of 2. So this is the composite of inverse functions, so we just get 0.0375t equals ln of 2, or t equals ln of 2 divided by 0.0375. And so let's take a calculator. This is what calculators are for. We certainly dealing with things like this. So I've got ln of 2 divided by 0.0375, and let's enter that and see what we get back. And it's equals approximately 18.5 years. And let's see, we need a year for that? No. So that's good. We've got it.